Let's take a look at sections 1.5 and 1.6. This is sort of a combined lesson. And the topic is limits and continuity. And so today we officially begin the calculus portion of our course. So we're going to define what a limit is, one-sided limits, two-sided limits. We're going to find values of limits by using tables and functions and algebra and graphs, all of those. And we'll do limits with infinities, and then we'll define what continuity is and how that works with limits as well. All right, so to motivate the idea of a limit, I want to take a look at this first function here. Example number 1. Let f of x equal 2x minus 18 divided by the square root of x minus 3. And the first question that we need to answer is this function defined at x equals 9? So in other words, is f of 9 defined? Well, of course, you could just plug it in. Let's take a look. So we're going to get 2 times 9 minus 18 divided by the square root of 9 minus 3. And let me do the bottom here. The square root of 9 is 3 minus 3. And that's 0 on the bottom. So that's a no. So is it defined? The answer is no. F of 9 is undefined. And the reason is because there is a 0 in the denominator. And this goes really well with what we did earlier with finding domains. If you have a value of x that makes the denominator equal to 0, then you can't use that in the domain, which means therefore the function is undefined. So that's nice, but is that the end of the story? Well, not quite. Let's take a look at the numerator. What happens up here? 2 times 9 is 18 minus 18. That's also 0. So notice I didn't need to know what the numerator was to determine that the function was undefined. But now that I know that it's 0 on top, that is something sort of very special. And that's where limits come in. So let's take a look at some other evidence, some other things that are going on with this function. So I know that I can't evaluate this function at x equals 9. But maybe I could determine what happens to the y values as I get closer and closer to 9. So here's a table of values, and I want to complete this table of values with the function above. And we'll demonstrate this in the calculator. And so when you type in that function, and then you go to table, you can change the table to table set and change the independent variable to ask. And when you change it to ask, that allows you to enter these different x values because there's no pattern where it goes up by 1 or 0.1 or anything like that. So we want to change it to ask. And then we'll just enter each of these values separately and come up with the y value. And they are 11.967. 3 decimal places or more, if you need them, would be appropriate here. Next one would be 11.997. And then if we evaluate at 8.999, we get 11.9997. And then we evaluate at 8.9999, we get 11.99997. And we could continue to get closer and closer to 9, but as soon as we hit 9, we know that that's undefined. But notice that these values sort of form a little pattern. If I sort of go from the left here, moving toward 9, I can tell that these numbers are getting closer and closer to 12. And that's what this statement says here. As x approaches 9 from the left, meaning that these values that we're using are all slightly smaller than 9, but they're getting closer and closer to 9. Then the y values are going to approach 12. Well, if I do this the same thing, but now I use values on the right side of 9, I'm going to use 9.0001, and I'm going to get 12.00003. And then I can plug in 9.001 and get 12.0003. 9.01 yields 12.003. And then 9.1 is 12.033. And this time, we want to think about x approaching 9 from the right, where the values are all greater than 9. So this time, it looks like we're going this way. And you can see that these numbers are getting closer and closer to 12. Now, 12 is not the value of the function at x equals 9. Remember that the value of the function is undefined. But what we have here is called the limit. And the limit considers what the function values are approaching as the x values get closer and closer to certain numbers. Now this top one up here, this is going to be called the left limit. And the bottom one here is going to be the right limit. And these are the one-sided limits. So let's write that down. So the left limit has this notation here. It's LIM for limit, and then immediately under that you put X, arrow, and then whatever your target number is. I use C to represent the target. And then you're going to use a superscript of a negative sign. And that superscript indicates that this is the left side of X equals C. And you always have to tell it what function you're dealing with. And then it's equal to some value if it exists. And what this means is that the values of the function f of x get closer and closer to L1, that's called the limit, as x gets closer and closer to C with the x's less than C. And then we have the right limit. And this is the limit as x approaches C. Now think about what symbol should I use for the superscript to indicate the right side of the target. If you said the plus sign, you are correct. And then that's f of x is equal to L2. Now this is a different L because it might be a different value. And we'll see some examples of that as we go forward. But this definition is basically the same, it's just to the other side. So it's the values of f of x get closer and closer to L2 as x gets closer and closer to C with the x values greater than C. So those are our left limits and our right limits. So now let's go back to the chart here. So what is the chart saying? Well, the chart is actually saying this. This left limit says the limit as x approaches 9 from the left of the function 2x minus 18 over the square root of x minus 3, that is equal to 12. And then the right limit says the limit as x approaches 9 from the right of the function 2x minus 18 divided by the square root of x minus 3 is equal to 12. So those are our two one-sided limits. Now, in the case where the two one-sided limits are the same value, that produces the whole limit. The two-sided limit, the whole limit, or just the limit. And so that says the limit as x approaches c of f of x is equal to L if and only if both one-sided limits exist and have the same value. In other words, they're equal. So, in other words, the limit as x approaches c of f of x is equal to L. This is equivalent to saying that the limit as x approaches c from the left of f of x is equal to L, which is equal to the limit as x approaches c from the right of f of x. So if the two one-sided limits are equal, they exist and are equal, then we can put those together as the two-sided limit, the whole limit, and make one simple statement. They have to be both equal to the same value. Okay? And conversely, if I know that the limit exists and is equal to L, then that also tells me that the two one-sided limits exist and are equal to that same value. Notice that for the whole limit, there is no superscript right here like there is in the one-sided limits. You just write x approaches c, and that's it. Let's take a look at some examples. So example number 2, use the graph to compute the following limits. Part A is what is the limit as x goes to 3 from the left of f of x. So as I follow the graph, the actual graph of the function, right, on the curve, and I get closer and closer to 3, you're looking for the y value that is approached. And you can see that 3 has an anchor point. So as we get closer and closer to where x is equal to 3, by staying on the left side of x equals 3, it gets closer and closer to the value of 2. Remember that limits are the y values here. Part B, the limit as x goes to 3 on the right side of f of x. Well, we follow the curve on the right side, and as we get closer and closer to 3, we can see that the y values are approaching 4. Part C, the limit as x goes to 3 of f of x. This is the two-sided limit. Now the two-sided limit exists only if the two one-sided limits exist. Well, these are not equal. So that means that this limit does not exist. And we write D and E. So D and E stands for does not exist. And finally, f of 3 would be where is the function value for this graph? Well, function values are denoted by solid dots. And we see that there is a solid dot when x is equal to 3 at the y value of 6. So you can see that the function value and the limit values do not necessarily have to be anywhere close. They don't have to be connected at all. That's the beauty of the limit versus the function value. So this was sort of the major problem that was solved by limits. They wanted to know what the function values were approaching, but not necessarily what the function value was. So thus enter the limit. Example 3, use the graph to compute the following limits. So example part A, the limit is x goes to 4 from the left. So as I follow the graph down toward where x is equal to 4, we can see that we approach the y value of 2. Part B, the limit is x goes to 4 from the right of f of x. We can see as we trace the graph going back toward x is equal to 4, we get closer and closer to a y value of 2. And now to determine if the limit exists, we examine the two one-sided limits. They are equal, so that's great news. That means that the whole limit exists and is equal to that same common value. So the answer for the limit itself is 2. Now this is characteristic of what a limit will look like on a graph. If you trace both sides coming in toward where x is equal to 4, they intersect. Even though there's a hole there, that's okay. The limit does not care what happens at that particular point. It just cares about what the y values are doing as you get closer and closer to that point with the x's. And then finally, part D, f of 4 is where's the solid dot? Solid dot is at 1. Example number 4, use the graph to compute the following limits. So A is the limit as x goes to 2 from the left. So if I follow the graph from where x is less than 2 and it approaches 2, we see that we have a vertical asymptote at x equals 2. So the function values are actually going to go up to infinity. So the limit is infinity. Part B, the limit as x goes to 2 from the right. Well, as we trace the graph here, we're still approaching that asymptote, but they're going down. So now we would say that that is going to negative infinity. And then lastly, for this part of the deal, the limit as x goes to 2 of f of x. Well, these are different values, let's say. So that's infinity and negative infinity. So this one does not exist. Now I should mention something. The limit exists when it is equal to a finite number. So technically, this does not exist either. But anytime you get to supply extra information about what the limit is doing and what the behavior of the graph is, you go for it. So saying that a limit is equal to infinity is not implying that the limit exists, because it doesn't, because it's not approaching a single number. Rather, it's describing the behavior of the graph, and in this case, the first one is going sky high, and the bottom one is falling off a cliff. F of 2 is undefined, because that's where the vertical asymptote is. So here's another point of contention. When it doesn't work for a limit, we say does not exist. And when we say it doesn't work for a function, we say it's undefined. Okay. So you don't say that a function does not exist. We don't really say that. We say it's undefined. And we don't say that a limit is undefined. We say that the limit does not exist. The final two questions here, the limit as x goes to negative infinity of f of x. Well, x going to negative infinity is talking about the left side end behavior. So what does the graph do as you head off toward the left side of the graph? Well, as I trace the graph here, you can see that the graph is going to settle in. It has a horizontal asymptote at 0. So the function values are getting closer and closer to 0, and we have an asymptote there, so they get closer to 0, and that's the limit. Same thing for this one, except x going to positive infinity is the right side in behavior. So as we trace out the graph going to the right side, it levels off to where y is equal to 0. Let's look at limits with algebra. So here's our guide box. In order to find the limits using algebra, first you want to try to evaluate the target number c in the function. And if it evaluates to a number, then that's the limit. And you're done. That's sort of the perfect scenario. If you can plug in the number and it works, that's it. That's also the limit. But if when you try to evaluate and it doesn't work because it's undefined, then, and it's because there's a 0 in the denominator, then what you can do is you can try factoring and canceling and then try to evaluate it again. So let's look at example number 5. Find the limit as x goes to -5 of x squared minus 7x minus 1. So the first thing you want to do is rewrite the problem. And we try part 1 evaluation. So we evaluate -5 squared minus 7 times -5 minus 1. That's equal to 25 plus 35 minus 1. And that would be 59. So because it worked, that's the limit as well. So everything is good for that one. Example number 6. Find the limit as x goes to 7 in x squared minus 49 over x minus 7. So let me write out the problem. And then let's try to evaluate. So we get 7 squared minus 49 over 7 minus 7. Well, 7 squared minus 49 is 0. 7 minus 7 is 0. So this is not good. It's not bad, but it's not good. And let me warn you about the biggest mistake I see in this class, in this section, all the time. As soon as you get this, some people like to say, well, it does not exist. No, that's not necessarily true. If it's 0 over 0, there are ways that we can handle that. So it's not, does not exist. Some people like to say that it's 1 because anything divided by itself is 1. No, that's not true either. It's true for everything but zeros, but when it's 0 over 0, it's indeterminate is what we say. And so then we can use the limit stuff. And then, of course, some people like to say, well, it's 0 because it was 0 divided by something. No, might be 0, but you don't know that it's 0. And it's not 0 because it's just 0 over 0. So not all of those are bogus. That's no good. That's not going to work. So we use rule 2, factor and cancel. So let me write the problem again. So the limit is x goes to 7 of x squared minus 49 over x minus 7. And then we have the limit as x goes to 7. And we're going to factor the top. This is the difference of two squares. And so x squared minus 49 factors as x minus 7 and x plus 7. And then I can cancel the x minus 7s. And that leaves me with the limit as x approaches 7 of x plus 7. And now we can try to evaluate again. And this time it works. I plug in 7 for the x. I get 7 plus 7. And the answer is 14. And that is the limit. There's a couple of ideas here that we want to emphasize. Repeating. 0 over 0 is not an answer. It's not great, but it's not bad because you can then do more things to solve it. So maybe a reminder here, not done, right? This is not the way to finish a problem, 0 over 0. The other part that we want to emphasize is notice where the limit notation is used and when the limit notation is dropped. You might want to think about the limit notation here as being part of your to-do list, right? When do you mark something off of your to-do list? Whenever you have done it, right? So what is taking the limit? Well, taking the limit is the process of taking the number and evaluating it in for the x. So this is the step right here where the limit is performed. Everything else is preparation. And so you're trying to get it set up so that you can take the limit by plugging in the number. So you write the limit on the first part, you write the limit on the second part, you write the limit on the third part, and then this part right here, where the limit is performed, is where you drop the limit notation. Okay? Now that is going to be part of reading your homework and assessing your understanding of the limits, is when do you drop the limit notation? In other words, when do you actually take the limit? And are you able to communicate that to your reader? Okay. The other part to always remember is equal signs. Notice there's equal signs at every level here, and that we started with the original problem. Don't just jump in and start with something that is sort of secondary. Start with the original problem that you are trying to solve, and then start to solve it, right? Because you are supposed to provide a complete solution. The person who's reading your homework should be able to understand what the problem was without ever having to see the problem, right? They should be able to read your solution to understand what's going on. Example number 7. Find the limit as w approaches -1 of w squared plus 4w plus 3 divided by w squared minus 4w minus 5. So there's something. You don't have to use x's. You can actually use whatever variable you'd like. So let's work this one out. We start with the evaluation phase. So the limit as w approaches -1 of w squared plus 4w plus 3 over w squared minus 4w minus 5. Let's try evaluation. So we get -1 squared plus 4 times -1 plus 3 divided by -1 squared minus 4 times -1 minus 5. That gives us 1 minus 4 plus 3 divided by 1 plus 4 minus 5, which is 0 over 0. All right, so again, that's not an answer. It's not great, but it's not bad. We can work with it. So now let me try the limit with factoring and canceling. So w squared plus 4w plus 3 divided by w squared minus 4w minus 5. Remember to write the limit as w approaches -1. And let's see here. So w and w. What two numbers multiply to give you 3 and add to give you 4? That would be +1 and +3. And on the bottom, w and w. What two numbers multiply to give you 5 and subtract to give you 4? Well, that would be 1 and 5. And the 5 should be negative, and the w with the 1 should be plus. Now, let me take a pause here to sort of show you the algebra part, how it's working out. You notice that you had 0 over 0 over here when you tried to evaluate. That means there is some factor in the numerator and in the denominator that is producing this 0. And then there can be other factors that you multiply and they don't count because, 0 times 46 is still just 0, whatever it would be. So the question is, what factor creates a 0 whenever you're trying to evaluate w approaches -1? Well, that's the factor of w plus 1. Because negative 1 plus 1 is equal to that 0. That's where that 0 is coming from. So you should expect these w plus 1 factors to be inside this factorization. It shouldn't be a surprise and it shouldn't be a mystery because you had to get 0 over 0 somehow, and this is how it happens. Now, you may not get it on the first try. You may have to do multiple factorings, but usually we don't get that complicated in this class. But that's possible. But it's in there somewhere. And in fact, this w plus 1 divided by w plus 1, those are the factors that are causing all the problems. So once you cancel and get rid of those, then you're good. We can now continue working with the limit and come up with something. So I've canceled those off. That leaves me with the limit as w approaches negative 1 of w plus 3 divided by w minus 5. And then we can evaluate. So we get negative 1 plus 3 over negative 1 minus 5. That's equal to 2 over negative 6, which is negative 3. And it's negative 1/3. So that's the answer. Let's look at example number 8. Find the limit as x approaches 2 of x squared minus 5 over x minus 2. So again, we would try the evaluation. So the limit as x approaches 2 of x squared minus 5 over x minus 2. That would be 2 squared minus 5 over 2 minus 2. So that's 4 minus 5 over 0, which is negative 1 over 0. Okay, so that's pretty bad. Yeah, so we got a 0 here. And so this limit is not going to exist. So we're going to say right now does not exist. This is going to be my temporary answer because we're going to learn some techniques later on in this section about how to handle this. But I did want to show you what it would look like if you still got a 0 on the bottom, but you didn't get a 0 on the top. Like I said earlier, the reason that the top one worked out so well is because you had both factors in the top and bottom and they canceled. Well, this time you don't have that factor in the top. So it's not going to cancel by factoring. And so it's going to not exist. But then there might be some other things that we can say about it, and we'll talk about that a little bit later on in this section.